Hello James! After a long time, welcome back to A series. In this video of A series, we are going to discuss previous year BITSAT questions from the chapter of moving charges and magnetism. I hope you know that your BITSAT dates are released. Your BITSAT 2021 will be conducted from 3rd of August to 6th of August. Okay, so we have 1 month to hustle. Also, I hope you are all set with your preparations. You are giving your mock tests regularly. If you are not, pull up your socks. It's high time to do so. Let's begin with today's class. So question 1 and 2 over here, questions from the super easy category. Okay, so in question 1 you are asked for the torque on a current carrying loop which is placed in an uniform magnetic field. Okay, so here the letters have their usual meaning. M is for magnetic dipole moment and B is for magnetic field. Okay, so actually there is a whole derivation to this thing. Okay, torque on a loop, current carrying loop placed in an uniform magnetic field. Okay, the end result of the derivation is something that you should know. Okay, the end result that you get is your answer over here. The torque on a current carrying loop placed in an uniform magnetic field is M cross B. Okay, you might in fact know it as a formula that tau equals M cross B, right? Tau equals M cross B. It's just a formula over here, no more logics, right? It's just a formula, tau equals M cross B. So option C is the correct choice over here. Let's move to question 2. Now in question 2 you have two infinitely long current carrying wires. The current is as shown. Okay, it is given that these two wires attract each other. You are supposed to tell why. Why does this happen? Why does these two wires attract each other? We know this, right? Parallel currents attract each other, right? But why? Okay, why? The nation wants to know why. So you can see that basically these two wires are attracting because there is a force between them, right? The force on wire 2, suppose this is wire 1, this is wire 2, so the force on wire 2 is towards wire 1 attracting. Also the force on wire 1 is towards wire 2. Okay, so the force are towards each other. Okay, so they seem attracting each other. Okay, now question 2, is the force electric or is the force magnetic? You can easily see that the force is magnetic in nature. How can I claim that? See, let's look out for wire 2. You can see that wire 2 experiences force due to two reasons. One, because it is carrying current. Okay, agreed. And second, because it is placed in the magnetic field created by wire 1. Okay, so you can see that wire 2 is experiencing force because first of all it's carrying current, and second it's placed in the magnetic field created by wire 1. Okay, so you can use your right hand palm rule and find the direction of force, and as I said it will be towards wire 1. Okay, but the question is not that over here. The question is why these two wires attract each other. It is because there is a force between them and the force is magnetic in nature. Okay, or basically magnetic force between the two. Okay, so option D is the correct choice over here. Yes, option D is the correct choice over here. I forgot to mention Gem Army goes red today. Okay, so enjoy the red edition. Over to the next set of questions. So question 3 and question 4 over here, we are still there in the super easy category. So in question 3 you are given a region of uniform electric field and uniform magnetic field. The region is suppose the plane of this board. Okay, so in this region you have uniform electric field and uniform magnetic field. The direction of both the fields is from left to right. Okay, the direction of both the field, the electric field as well as the magnetic field, is from left to right. Okay, now you are going to release an electron with velocity v in the same direction as that of the fields. Okay, so you are going to release the electron in the same plane of this board in this direction from left to right. Okay, you are supposed to predict the motion of this electron. What will happen to this electron? Will it turn right, turn left? Will its speed increase or will its speed decrease? Okay, so first of all you can see that there will be no force on this electron due to the magnetic field. Why? Because if you see the force due to the magnetic field is QVB sine theta or QV cross B, and the angle between V and B is 0 degrees, right? They are parallel. V and B is parallel. So QVB sine 0. Theta is 0 over here, right? V and B are parallel. Theta is 0, sine 0, 0. Okay, so the magnetic force is 0 over here. Okay, so the force on that electron due to the magnetic field is 0 because the motion is parallel. Now you can see for the force on that electron due to electric field. Okay, so you can see that force on that electron will be minus EE. Okay, let's write it vectorially. Okay, so this is the elementary charge and this is minus. Okay, minus because it is electron, right? So you can see that force will be opposite to the direction of the electric field, right? It is electron, we know this, right? So its velocity is in this direction. Force will be in opposite direction to the electric field. Electric field is from left to right, right? Force is opposite because this minus sign shows that. Okay, force is opposite to the direction of electric field. Okay, so force is in this direction. So force is in this direction, or can I say that acceleration is in this direction, right? Okay, so acceleration is in this direction. So you can see that this is negative acceleration, right? Negative acceleration, or you can call it retardation. So you can see that velocity is in this direction, acceleration is in this direction, velocity is from left to right, acceleration is from right to left, the motion is retarded, right? So the speed of that electron will decrease. So option D is the correct choice over here, right? So velocity is in this direction, acceleration is opposing the motion, right? So speed will of course go on decreasing. Okay, so option D, speed will decrease, is the correct choice over here. Now let's come to question 4. So in this question you have a charge, you also have a uniform magnetic field region over there. Okay, the magnetic field is as shown. I hope you know what this means. This means that the magnetic field is inward into the plane of this board. Okay, so magnetic field is inward. You are going to release a charge in the plane of this board and from left to right. Okay, so it will perform circular motion over there. We know this, right? So you are supposed to tell what is the now what will be the power delivered to this charge depend on. Okay, what will be the power delivered to this charge depend on. Okay, this is a question from 2018, a recent one. Now I know you might be tempted to say it will be force and velocity because you know that power is F dot V, right? Power is F dot V. So you will say power is power depends on force and velocity, which is wrong because power is F dot V. So it is Fv cos theta. It also depends on the angle. Okay, and if you see over here, let's find the direction of force. We want the Fv cos theta, right? Power is Fv cos theta. We want to know the angle between F and V. Okay, basically you can see that it is uniform circular motion, right? F and V will have an angle of 90 degree. Okay, let's prove that. Okay, so B is inward, V is in this direction. Okay, so F will be in the upward direction. I am using the palm rule. You can also use your FBI, Federal Bureau of Investigation. Nice way to remember. Okay, so FBI, so B goes inward, FBI. Okay, V. Okay, so V in this direction, motion of the charge flow. V in this direction, force will be in the upward direction, as I said by the palm rule. Okay, in the upward direction. Okay, so force is in this direction and velocity is in this direction. You can see that force and velocity will be always perpendicular, right? It will perform circular motion, uniform circular motion. Force and velocity will be always perpendicular. So F V cos 90. Cos 90 is 0, which means power delivered does not depend on force and velocity. It will be always 0. Okay, so option D, none, is the correct choice over here because it's always 0, right? It does not depend on this factor. There was one more way of looking at this. You could see the work done. Okay, you can see that the force is in the upward direction. You can find it out using the palm rule similarly. Okay, so force is in the upward direction and you can see that displacement is always perpendicular, right? It will move in a circular motion, right? So force and displacement are always perpendicular. So you can see that f d cos theta, which is the work done, f d cos theta, that will be 0, right? Because f d cos 90, force and displacement perpendicular. So f d cos 90, 0, work done 0, no power delivered, right? So power delivered in this case will be 0, and it does not depend on force and velocity. Keep that in mind. Let's move to the next set of questions now. So question 5 and 6 over here, we are still there in the super easy category. Okay, so many super easy category questions today, right? So anyways, let's come to question 5. In question 5, we have a region of uniform magnetic field. Okay, the direction of the field is as shown, it is inwards, okay, into the plane of this board. You are supposed to find the net force on a current carrying circular loop which is placed in this magnetic field. Okay, find the net force on a current carrying circular loop which is placed in this uniform magnetic field. That is the question. Now if you can recollect the first question that we did today, it asked you for the torque, right? Torque on a loop which is placed in an uniform magnetic field. Okay, that had some value m cross b, we know it, right? But what about the force? If you can recollect the derivation which I mentioned over there, okay, the net force on that loop is 0. Okay, net force in that case is 0. You have two equal forces acting along different lines which generate the torque. Anyways, the net force on that loop is 0. Okay, so here also same thing happens. The net force over here is 0 as well. Okay, you can actually see it through your right hand palm rule. You can see it through symmetry that two diametrically opposite forces will cancel out each other. Okay, so you can see that here the force will be inward, here it will be downward, inward, inward. Okay, so two diametrically opposite forces will cancel out each other. Okay, you can see it through symmetry. You can use your right hand palm rule or the left hand rule to do that, but here I'll make a bold statement which you should remember. Okay, the statement is that net force on a current carrying loop placed in an uniform magnetic field is always 0. Okay, I'll repeat it. Net force on a current carrying loop placed in an uniform magnetic field is always 0. Okay, the only condition is that the loop should be closed. What am I saying? Loops are always closed, right? So no condition as such. Okay, so loop can be any shaped. You can have any random shaped loop. Okay, the net force on that loop will be always 0. Okay, you need not always look out for symmetry. The net force on any current carrying loop placed in an uniform magnetic field is always 0. Okay, so not just circular, any randomly shaped loop, even a heart shaped loop will do it. Okay, the net force on any loop will be always 0 provided it is placed in an uniform magnetic field. Okay, so 0 is the correct choice over here. Here you can also see it through symmetry using your right hand palm rule or left hand rule. Okay, but that is for kids. We do it this way. Now in question 6, we have a current carrying wire which is carrying current from east to west. Now I know, like a moron, I have drawn it in the wrong plane. The correct plane is the horizontal plane, right? East, south, north, west is in this plane, not in the vertical plane. Okay, so east direction over here, west direction over here, the wire is carrying current from east to west. Okay, so you are supposed to find the magnetic field at ground. Okay, magnetic field at ground. Also find its direction. So first of all, let's find the direction of the field. You can use your right hand thumb rule, your thumb in the direction of the current and curl your fingers. You can see that the direction of the field is towards you, right? The direction of the field at ground is towards you. You can see this is east direction, this is west direction, north is in front, south is towards you, right? East, west, north is in front, south is towards you. Okay, so the direction of the field at ground is towards you, which means it's in the south direction, right? So option B and option D, get out of the way. Okay, north is not the correct direction of the field. Okay, the field is in the south direction. Now let's find the magnitude of the field. The magnitude will be given as, now you can treat this wire as infinitely long. Okay, so mu 0 upon 4 pi 2I by r. Okay, so mu 0 upon 4 pi, this is the formula for magnetic field due to an infinitely long wire. Okay, so mu 0 upon 4 pi, that is 10 to the power minus 7 into 2 into I is 100 divided by r. R is the perpendicular distance, which is 4 meters over here. So 2 2s are 4, 2 50s are 100. Okay, so 50 into 10 to the power minus 7, or I can write it as 5 into 10 to the power minus 6. So 5 into 10 to the power minus 6 Tesla south is the correct choice over here. Okay, so option C is the correct choice over here. You can see that this question has repeated over the years, once in 2006, then again in 2012. Okay, just simple formula based question. Okay, so let's move to the next question now. Okay, so that's all from the super easy category. Okay, so we'll step up the level now, so get ready. So question 7 over here, now from the easy category. Okay, so we have just stepped up the level a bit. Okay, so in this question you had a wire of length L. You were not happy with it, so you made a loop out of it. Okay, now you made current flow through it. You were still not happy, so you placed it in a uniform magnetic field. Okay, so the direction of the field is as shown, inwards. It is an uniform magnetic field. You are supposed to find the maximum torque on this loop. The fire was great, right? Anyways, so find the maximum torque on this loop. So maximum torque, first of all, torque on a loop, we know it from question 1. It is given as m cross b, right? Or we can write it as mb sine theta. Okay, so mb sine theta, maximum torque will be mb, right? Maximum torque will attain its maximum value when sine theta becomes 1, right? So the maximum torque is mb over here. Okay, so m is given as Ia. One more formula, you should know this. M is given as Ia. Okay, so the current flowing in the loop into the area vector. Okay, so into B. So IAB. You might also know it as formula of torque, right? Torque equals IAB. Okay, so now how to find the area? This is a circle, right? Circular loop. So area will be given as pi r square. Okay, so I pi r square into B. But we don't want this answer in terms of r. Okay, we are not told that the radius is r. This is something that we assume, right? So can we express this r in terms of L, right? We know that we made this loop from this wire, right? Initially we had the length L, right? We had a wire of length L. We made loop out of it, which means the circumference of this loop, will be equal to the length of the wire with which we began, right? The circumference of the loop will be equal to the length of the wire. The circumference will be equal to the length of the wire. So the length of this wire will be equal to the circumference, which is 2 pi r. This r is the assumed radius over here. So you can find the value of r over here. R will be L by 2 pi. Okay, so L by 2 pi. So just substitute r over here and you'll get your answer. Okay, so I pi, and in place of r square you put this L square by 4 pi square. The squaring this, okay, r square. So L square by 4 pi square, right? This and this will get cancelled, and here you have b, right? So I L square, I'll write it in a better way, I b L square by 4 pi. Okay, so I b L square by 4 pi. So option A is the correct choice over here. I b L square by 4 pi. Okay, so we just use the formula for torque. A little bit of logic over here. Circumference equals to the length which we began with. Okay, so the answer that we get is I b L square by 4 pi. Okay, so that is the answer. Option A is the correct choice. Let's move to the next question now. So question 8 over here, in this question you are supposed to find this current I. Okay, actually conceptually this question belongs to moving charges and magnetism, but if you go to solve it, it's just a matter of your current electricity. Okay, because you know that current will be given as V by R equivalent. So you just have to find the equivalent resistance over here and then V by RE, and that's how you get your answer. Okay, but I'll go ahead and accept and explain the conceptual aspect over here. So here if you see, we have a galvanometer. Okay, here the galvanometer is converted to ammeter using shunt resistance. Okay, galvanometer with some high resistance, and then we use shunt resistance in order to convert it to ammeter, right? But it's not ideal. So if it was idle, okay, if suppose this was idle ammeter over here, you can see that the current will be 3 by 3, right? Idle ammeter, the resistance will be 0, right? The current will be V by R, so V by R, that will be 1 ampere in case of idle ammeter. But here if you see, the answers are less than 1 ampere. Why is that so? Because this is a galvanometer which we have converted it into an ammeter, which is of course not idle. Okay, so anyways, all that you need to know is this V by Re, okay, in order to solve it. So Re, first of all, you can see that these two are in parallel combination, right? Shunt is connected in parallel to convert to ammeter. Okay, so parallel combination, product upon sum, 60 into 0.02 plus 60, 60 plus 0.02, that will be 60.02. Okay, so I can just treat it as 60, right? Instead of writing it as 60.02, I can just treat it as 60. Okay, approximating. Okay, so this and this will get cancelled, and you can see that the resistance will be approximately 0.02. Okay, here the resistance here will be 0.02. These two are in parallel combination, right? The resistance actually, if you go to calculate it, will be less than either of the two. Okay, but here we have made some approximation, and that's why it's coming close to this one, coming equal to this one, 0.02 ohms. Okay, and now this 0.02 ohms is in combination, in series combination with this one, 3 ohms, right? So plus 3, so 3 plus 0.02, that will be 3.02 ohms. Okay, 3.02 ohms. So this is the equivalent resistance over here. Okay, this is the 0.02 is the equivalent of this two, and then finally 0.02 plus 3, that gives you 3.02. that is the equivalent resistance over here. So the current will be given as 3 by 3.02. okay, and which will be approximately very close to 0.99. okay, 3 divided by 3.02, almost close to 1, right? But not 1. okay, I hope you are getting that point if you listen to the conceptual aspect very clearly. Okay, so option C, 0.99 amperes is the correct choice over here. I think this is one of your NCRT examples. Okay, you can look into your NCRT. I think exact values are used in your NCRT as well, and the same concept is explained there as well. Okay, so 0.99 is the correct answer over here. Over to the next question. So question 9 over here, in this question you are given that maximum reading of a ammeter is 1 ampere. The resistance of this ammeter is 0.81 ohms, not an idle one of course. You have to increase the range of this ammeter so that it measures a current of 10 amperes. What is the shunt resistance that should be connected in parallel in order to achieve this? Okay, basically if you see, it is the same concept of galvanometer. Okay, don't get confused with names. This is just the same concept that you use for conversion of galvanometer to ammeter. That same concept you have to apply over here. What do we do when we convert a galvanometer to an ammeter? We just increase the range, right? If you see, galvanometer is also capable of measuring current, right? It measures current in amperes, small currents, right? We just increase the range by connecting the shunt. So here also we have ammeter. We have to do the same thing, right? We just have to increase the range. Okay, so basically the same concept. Okay, it just in place of ammeter, in place of galvanometer, they have used ammeter. So don't get confused by it. The purpose is the same, which is to increase the range, right? So let's find the shunt resistance. How do we do that? There is a formula for it, conversion of galvanometer to galvanometer to ammeter. Okay, the formula for shunt resistance is IgG upon I minus Ig. Okay, so Ig is the maximum deflection current. So maximum reading of this ammeter is 1 ampere. Okay, now resistance of the galvanometer, here we'll use resistance of the ammeter. Okay, analogous 0.81. Okay, the current that we want to measure, I is the current that we want to measure, which is 10 minus the Ig. Ig is the maximum current again that is measured by the ammeter, which is 1. Okay, so you can see that it will be 81 into 10 to the power minus 2 divided by 10 minus 1, 9. 9 nines are 81, and 9 into 10 to the power minus 2, which is 0.09 ohms. Okay, so option D, 0.09 ohms is the correct choice over here. Okay, so yeah, let's move to the next question. So question 10 over here, in this question you have fired a beam of protons and neutrons having same momentum in a region of magnetic field. Directions as shown, you are supposed to tell the ratio of radii of their circular paths. Okay, so you'll know that the radius of the orbit in which they are going to revolve is given as mv by qb, right? Okay, radius is given as mv by qb. This is obtained by equating the centripetal force to the magnetic force qvb. Okay, so here the radius will be mv by qb. You can see that mv is nothing but momentum, right? mv is mass into velocity, which is momentum. Okay, so I can write r equals p by qb, where p is momentum, right? So p by qb. You can see that now you can see radius is inversely proportional to charge, right? Radius is inversely proportional to charge, because if you see in this case we have same momentum, both protons and neutrons have same momentum, and the magnetic field is also same for both, right? They are fired in the same magnetic field. So you can directly see that radius is inversely proportional to charge. Okay, now one thing to note over here is that if the charge on proton is q, charge on neutron will be also q. Okay, they differ in mass. Okay, proton, if they have mass m, neutron will have mass 2m. Okay, they don't differ in charge, they only differ in mass. Okay, so if proton has a charge q, neutron also has charge q. If proton has mass m, neutron has mass 2m, twice the mass of the proton. Okay, here the radius only depends on charge, so r1 by r2 will be q2 by q1, but that doesn't matter because q2 is q, q1 is also q, which means the ratio will be 1:1, right? Both of them have same charge, so q2 by q1 is 1:1. Okay, so option B, 1:1 is the correct choice over here. Make sure you remember this. We will use it in the next question as well. Some spoilers here and there. Over to the next question. So question 11 over here. So just like the previous question, here also you have fired a neutron and proton in a region of magnetic field. Directions as shown. The kinetic energy of neutron is 50 kilo electron volts. The radius of its circular path is 0.5 meters. Okay. Here also proton has the radius of the circular path of proton is 0.5 meters. Okay. You are supposed to find the kinetic energy of proton. Okay, here also same thing, we are going to use the radius formula. Okay, r equals mv by qb. Okay, and we know from the previous question that this mv can be replaced by p, the momentum. Now, do you know the relation between momentum and kinetic energy? Yes, you should know this, that momentum and kinetic energy, the relation between them is p equals under root 2 m. Okay, p equals under root 2 mk. Okay, so substitute it over here, so you get under root 2 mk by qb. You can see that magnetic field is same for both proton and neutron. Charge is also same, right? We know this. Charge for neutron, it's q. Suppose for proton it's q, then for neutron it will be q. mass of proton is m, then mass of deuteron twice, okay, dew twice, 2m, okay, mass is twice, not the charge. So mass is not same, charge is same, magnetic field is same, okay. So you can see that radius, you can write radius as directly proportional to under root mk, right? Everything else is a constant, right? 2 is constant, q is constant, b is constant. It's same for both, okay? So when you take the ratio, it will cancel out basically. So r1 by r2 will give you under root m1 k1 by m2 k2, right? Radius of your first deuteron by radius of your proton will give you under root m1 k1 by m2 k2. K1 k2 are the kinetic energy, respective kinetic energy. Okay, you can see r1 by r2, 0.5 by 0.5, okay, that will give you 1. So you can simply write under root m1 k1 equals m2 k2, right? M1 k1 equals m2 k2. Okay, so you can square on both sides, so you'll get m1 k1 equals m2 k2. Okay, so now just substitute the values, you'll get your answer. M1 k1, mass of the first one, let's take first one as deuteron, so 2m into k1 is 50 kilo electron volts into is equal to m2 mass of proton, we'll take it as m and m will get cancelled, into k2 is something which we have to find. Okay, so k2, so you can see 2 into 50, 100 kilo electron volts. Okay, so 100 kilo electron volts, option D is the correct choice over here. I hope the approach is very simple. Okay, first we reach P by QB, then we use the relation between kinetic energy and momentum. We substituted this, okay, and just wise manipulations from there. Okay, R1 by R2 equals under root M1 K1 by M2 K2. We solved it, we got our answer. Okay, now one more thing over here. You can see that both of them have the same radii, just like in the previous question, right? They had same momentum and therefore same radii. Now they have the same radii, right? 0.5 and 0.5. Okay, so will they have the same momentum? That is my question to you. You will answer this in the comment section. The correct answer will of course receive a heart from me. The question is, they have the same radii. So just like in the previous question, will they have the same momentum? Yes or no? Okay, over to the next question. So question 12 over here. In this question, you are supposed to find the magnetic field at point O. Okay, at this point O, where O is the center of the square. Okay, here you are given a square of side 2A. The current flowing in this loop, in this square loop, is I. Okay, so find the magnetic field at point O. Okay, you can clearly see that the magnetic field will be equal contributions of all these four sides. Okay, first of all, let's see the direction. Let's see direction one by one. Okay, let's take one side at a time. So let's consider this side first. So thumb in the direction of the current. You can see the magnetic field at point O is in the outward direction. Okay, right hand thumb rule. Here also, I'll put my thumb in the direction of the current. Here also the field is in the outward direction, right, towards you. At point O, it's towards you, not over here. At point O, okay, it's towards you. Now again, thumb in the direction of current, field at point O is towards you. Thumb in the direction of current, field at point O, not over here. Field at point O is towards you in the outward direction. Okay, so you can see that basically all the fields are in the same direction. Fields due to all the four wires, all the sides of the square are in the same direction, which means you can just add them. Okay, you can neglect the vector aspect since all the vectors are in the same direction. You can just add them. Okay, so you can just add them. That is one thing that we are going to do. And if you see it, due to symmetry, there will be equal contribution of each wire, right? The field at point O will be equal due to all the four wires, because this point O is at the center, right? So the field at point O will be equal contribution of this. So what I'm going to do is I'm just going to find the field due to one wire and then multiply it by 4. Okay, because it's equal contribution, as I said, right? And instead of calculating it each time, calculating the same value each time 4 times and then adding it. I'm just going to calculate it once and multiply it by 4, because I know due to symmetry there is equal contribution of field at point O. Okay, so let's find field at point O due to any one wire. Okay, let's choose this wire. Okay, the current in this wire is I. Actually, you could have seen the direction thing which I mentioned in one more way. You can see that the current in this loop is anti-clockwise, right? Anti-clockwise means the field should come outwards, right? Anti-clockwise outwards. Okay, so yeah, field was in the outward direction. This is a north pole, right? So field will be in the outward direction. That was one more way of looking at it. Anyways, let's come over here. Okay, so we are calculating field due to one wire and then we'll multiply it by 4. Okay, so field due to one wire, let's find it out. So first of all, we want this distance, right? The perpendicular distance of that point from the wire. So you can easily see that that distance will be A. How can I say that? So instead of using Pythagoras theorem over here, you can easily see that this side will be 2A, right? It is a square. It is a square, so this side will be also 2A. So this will be A and this will be A. It's the center, as I said. So A and A, right? A plus A, 2A. So this will be A. This distance of the point O from this wire will be A. Okay, I've shown it over there. Now let's find the magnetic field at point O. What's the big deal? Mu 0 upon 4 pi I by R. Now don't use the formula for infinite wire. This is not infinite wire. It is finite in length, right? It has some length 2A. Okay, it's finite in length. So we have to use the general one, which is mu 0 upon 4 pi I by R into sine theta 1 plus sine theta 2. Okay, so this is the general one. We are going to use this one. Keep that in mind. Okay, so what is theta 1 and theta 2? Let us draw it over here. Okay, so theta 1 is this angle and so theta 1 is this angle and theta 2 is the angle over here. Okay, so we have to find this theta 1 and theta 2, and since we know it is a square, it is no big deal. You can easily see that these two diagonals will bisect this angle over here. This angle is 90 degrees, so it will bisect, the diagonal will bisect this angle. It will be 45 over here. We have dropped a perpendicular. This is the perpendicular distance, as I said. So here we have a perpendicular. Here you can use angle sum property, 90, 45, 45, right? So here also it will be 45 degrees. So 45 degrees, 45 degrees and 90 degrees. That makes it 180. So basically finding using angle sum property, find this angle. Theta 1 and theta 2 will be also 45. You need not do it again. Okay, by symmetry, or you can see that these two triangles should be similar, right? So theta 2 will be 45. Theta 1 is 45, theta 2 is 45. Just substitute the values, get your answer. Okay, so mu 0 upon 4 pi I by R sine of 45 plus sine of 45. Sine of 45 is 1 by root 2 plus 1 by root 2. 1 by root 2 plus 1 by root 2, x plus x, 2x. So 2 by root 2. Quick math. Okay, so you'll get mu 0 I root 2, mu 0 I root 2 upon 4 pi R. Okay, mu 0 I root 2 upon 4 pi R. Okay, but you won't find any option as such because we have to multiply it by 4. This is just due to one wire. Okay, we have 4 of them, 4 sides of a square. Okay, so multiply this by 4. Okay, so when you multiply it by 4, okay, 4 times this value you do, b naught dash LC. Okay, 4 times b naught dash, this 4 and this 4 will get cancelled. And this 4 and this 4 will get cancelled. Okay, I'll do it. So 4 times this value. Okay, so mu naught I upon 4 pi R into 2 by root 2, that will be root 2. Okay, this 4 and this 4 will get cancelled. You can easily see that answer will be root 2 mu naught I pi R. What is R over here? R is the perpendicular distance. R is A over here. Okay, perpendicular distance. Okay, A. Okay, just substitute the it over here. Okay. So mu naught root 2 mu naught I upon pi a. Root 2 mu naught I upon pi a. Option B is the correct choice over here. I hope that is clear. It is very straightforward. Just a little bit of logic over there. Let's move to the next question. Question 13 over here. In this question, you are given two infinitely long current carrying wires, okay, spaced this way as shown. It is given that the magnetic field at point O is 0. Okay, magnetic field at this point is 0. You can see that magnetic field at point O due to this wire is inwards, right? And due to this wire at O, the field is outwards. Okay, so these two fields have opposing effects and completely cancel out at point O. Okay, so at point O, the magnetic field is 0. So you are supposed to find what is the current in this wire, what is the value of this I. Okay, so you can see that first of all, in order to cancel the field at point O, the value of this current I should be obviously greater than 10, right? So I can neglect some options from here. How can I say that? First of all, because see, this is this wire 2 has to cancel the effect of wire 1, right? First of all, you can see that this wire 2, this is wire 2 and this is wire 1. Okay, so wire 2 is spaced much more. Okay, it's spaced away from point O at a distance of 27 centimeters, right? And wire 1 is just at a distance of 9 centimeter. Okay, so distance factor is not favorable for wire 2. So in order to cancel the magnetic field at point O due to wire 1, it has to have more current than wire 1, because distance factor is first of all not favoring it, right? Distance factor for this one, see, magnetic field is inversely proportional to distance. Okay, even if you are not getting what I'm saying now, you'll be able to do it. Just wait for some time. Okay, so I said distance factor is not favoring wire 2, right? So current factor should favor, right? Current should be more than this wire in order to cancel the magnetic field at point O. Okay, so now how to do this? You just equate the magnetic field at point O as 0. So you'll say field due to wire 1 minus field due to wire 2 will be equal to 0, or you can just equate their magnitudes. The magnitude of field 1 equals magnitude of field 2 at point O. Okay, at point O, field due to wire 1 is equal to field due to wire 2. Okay, so here what will be the value? Mu 0 upon 4 pi I by, so the current in the first wire, the current is 10. So it's infinitely long wire, so 2I by R, right? So 2I by R, anyways that will not matter over here. So 2I by R, R is 9 over here. Okay, 9 centimeters. I'll keep it in centimeters. Centimeter on the both the side will get cancelled. Okay, so here also mu 0 upon 4 pi 2 current in the wire 2, which is I, cos divided by R. R is the distance. Now it's not 18, it's 27. Okay, distance from point O. Keep that in mind. Don't make silly mistakes over here. So it is 27 over here. Okay. So the thing that I was saying, right? The magnetic field is directly proportional to current, inversely proportional to the distance, right? So I1 R1 by I2 R2. You could have just used that. Anyways, all this will get cancelled. Mu 0 upon 4 pi. 2 and 2 will get cancelled. So 10 upon 9 divided by 10 by 9 is equal to I by 27. So 9 threes are, so I will be 30 amperes. Okay, so 30 amperes, option C is the correct choice over here. Okay, so just equate the magnitudes, substitute in the formula, then what is left? Okay, just substitute the values and you get your answer. Okay, don't mistake the value over here. It is 27, not 18, not the distance between the wires, distance from point O. Very obvious, right? Let's move to the next question now. So question 14 over here, now from the easy moderate category. Can't believe that so far we were only discussing questions from the easy category. Okay, so let's come to question 1 from the easy moderate category. So in this question you are given certain arrangement over here. You are supposed to find the magnetic field at point P. Okay, point P is over here. So I hope the arrangement over here is easy to understand. You can see two infinitely long wires carrying current I placed at a distance 2d. Okay, now a midline is drawn. This is D and this is D. So this is the midline over here. You move a distance x from the midline, okay, to reach point P. Okay, move distance x from the midline to reach point P. You are supposed to find the magnetic field at point P. Okay, I hope you understood that. So you can pause the video and give this question a try. So first of all, you can see that the magnetic field at P due to wire 1 is inwards, right? Magnetic field at P due to wire 1 is inwards, and magnetic field due to wire 2 at P is outwards, at P, not over here, at P, okay? At P is outwards, towards you, and here due to this wire it was inwards, okay? So B1 I can say it is inwards and B2 is outwards. Okay, so one field is trying to cancel the other, okay, or trying to decrease the magnitude of the other. So find the magnitude of B1 and magnitude of B2, then B1 minus B2 or B2 minus B1. What shall we do? It should be B2 minus B1, okay, difference, bigger minus smaller. Okay, bigger, this one will be bigger, right, because current flowing in both the cases is the same. And magnetic field, as I said in the previous case as well, inversely proportional to distance. Here you can see point P is closer to the wire 2, right? So wire 2, the magnetic field at wire 2 is more because this point is closer, right? Closer to wire 2. So magnetic field at point P due to the wire 2 is more. So B2 is more, B1 is less. It's far, right? For wire 1, the point P is relatively far. Okay, so let's find B1 and B2 and then B2 minus B1. Okay, so B1 will be infinitely long wire mu 0 upon 4 pi I by 2I by R. R is the perpendicular distance. It will be D plus X over here. So D plus X. Okay, B2 will be, now this is in the inward direction. B2 will be mu 0 upon 4 pi 2I, current is same, upon D minus X, right? This distance is D minus X. This is D plus X for B1, and this will be, this distance from point P is, this is D minus X, right? D minus X. Okay, so here we have D minus X. So what do we have to do? B2 minus B1 to obtain our answer. So you can see that what is common over here, mu 0 upon 4 pi 2I is common over here. So B2 is this one. So 1 upon D minus X minus 1 upon D plus X. Right. So you have to multiply this to D minus X into D plus X. That will give you, so the same thing over here. Let's just copy it, mu 0. Okay. And here we'll have D minus X into D plus X using identity D square minus X square. Okay, so here we'll have D plus X minus D minus X. Okay, so you can see that I'll open this bracket directly. Okay, so minus D, and here it will become plus X. Okay, I just open the brackets. So this and this will get cancelled, D and D will get cancelled. So you'll get mu 0 and here you'll get 2x, right? Mu 0 4I. Where can I write that? I'll write it over here. So B net is mu 0 2I, and here also you'll get 2x. Okay, x plus x, 2x divided by 4 pi upon D square minus X square. Okay, so mu 0 4I, I can cancel this 2, 2 and 4. Right, so mu 0 ix, so either option B or C, D square minus X square, pi D square minus X square, pi D square minus X square. Here it's plus, so option B is the correct choice over here. Okay, so mu 0 ix pi D square minus X square. So find magnetic field at point P due to wire 1, find magnetic field at point P due to wire 2, B2 minus B1, because B2 is more in magnitude. Okay. So yeah, that is how you find net field at point P. Okay, this is magnetic field at point P. Okay, so option B is the correct choice over here. Over to the next question. So question 15 over here. Here also you are given an arrangement. So you are supposed to find magnetic field at point O over here. Okay, so you have a semi-infinite wire, arc, and again a semi-infinite wire. Okay, so first of all, look out for the direction. Okay, in this type of question, look out for the direction. See if the magnetic fields are in the same direction due to all the elements. Okay, so first element, semi-infinite wire, field at point O, inwards. Okay, using right hand thumb rule, it's inwards. Due to the arc also, it's inwards. Okay, and due to the your other semi-infinite wire, it is also inwards. Okay, so field at point O, due to all the three elements, semi-infinite wire, arc, and semi-infinite wire, is inwards, right? So you can just add the fields. Okay, so you can neglect the vector aspect now since they are in the same direction. Okay, so let us find B1. Okay, we'll name it 1, 2, and 3. Okay, so let's find B1, magnetic field due to 1 at point O. Okay, this is at point O. So B1 will be mu 0 upon 4 pi. Now this is a semi-infinite wire, so it is mu 0 upon 4 pi I by R. Okay, I by R. Now this R is not this R. R here is the perpendicular distance. Remember that. Okay, so I have been mentioning it throughout the class. So yeah, so this R is the perpendicular distance over here. So it will be the perpendicular distance of this line from point O. Okay, so we'll just extend this wire. Okay, and let's find that. So I have extended that wire. Here we have that arc. This is 90 degrees. So you want to find this distance over here. Okay, this distance you want to find. Let's call it R, small r. Okay, so how can we do that? So I know that this will be 90 degree. Okay, I just now said it's the perpendicular distance. So this is 90. This angle will be bisected by this line. This will be 45. This will be 45. Okay, so this is 45. This is also 45. Okay, so we can use sine 45. Okay, we can obtain a relation between this r and this r. Okay, I'll use cos 45. Cos 45 is equal to r by r. You can easily see that, right? Cos 45 is the adjacent side upon the hypotenuse. Okay, so cos 45 is 1 by root 2. 1 by root 2 is equal to r by r. That r I'll bring it to this side. So small r is equal to capital R by root 2. Okay, small r is capital R by root 2. We used our logics over here. Okay, so here in place of small r we'll put capital R by root 2. That will go on top. Now instead of finding field at B3, okay, finding field of B3 at point O, what I will do is I'll just multiply this by 2. I know this is also a semi-infinite wire, right? It will produce the same field, right? You know that the current is the same, it's still I, capital I, okay? It's still I, and the distance, the perpendicular distance from point O is still same, okay? So yeah, I'll just multiply this in order to find B3 equal to B1. I'll write B3 equal to B1, okay? Now let's find B2. B2 will be interesting. So B2 will be mu 0 I. Now this is the arc, right? So I'll use the formula for circular loop. Okay, the magnetic field at the center of circular loop. It is given as mu 0 I upon 2 R. Okay, I is capital over here. Mu 0 I upon 2 R. But this is for a circular loop. Here we have 1/4 of it. Okay, a quadrant, 90 degree, or you can write 90 by 360, right? 1/4, we have 1/4 of the loop over here. Okay, 90 by 360, which is the same thing, 1/4. Okay, so I'm writing 1/4 directly over here. Okay, or you can write pi by 2 by 2 pi. Okay, so that will give you the same thing. So B2 is mu 0 I, I'll write it in this way. Okay, So what I will do, I will just multiply this by 2, okay, because b3 is equal to b1, sorry, b3 is equal to b1, okay. So we have to just add these two fields now, okay. We have already found out the field b3, b1, we have already added them up 2 times, right? So here you have to add it with b2, okay, in order to find the net field at point O due to all of these 3 elements, okay. So we have to add this and that, okay. So b net will be b1 plus b2, or what I will do is I'll write this as b1 dash, because it's not actually b1, right? We have multiplied it by 2. Now just add this and you'll have your answer. So what can we take common? So here if you see, everywhere they have taken mu 0 upon 4 pi common, okay. So I am adding this and this, keep in mind. So mu 0 upon 4 pi, if we take common from both the things, okay, so mu 0 is common, 4 pi is common, what will be left with? So here we'll have, so I is also common, okay, I is also common, good enough. R is also common. So these things I have taken common, mu 0 I upon 4 pi r, okay. So here we will have 2 root 2, okay, 2 root 2, and from here since we don't have a pi over here in the denominator, I'll multiply it by pi, okay. Since I took common, okay, we didn't have pi over there, I took 4 pi common, we don't have pi over there, so I'm multiplying it by pi. You can open up and things will get back over here, okay. Pi and pi will get cancelled, you will reach back over here. So pi, and what is left over there, I took 4 common, I is common, r is common, so 2 is left, okay. So mu 0 I upon 4 pi r, 2 root 2 plus pi by 2, is it none? So let us try one more. Here the I should be capital I, sorry, okay. Let's try one more thing. What I want to do, I can see it's hidden over here, right? If you take 2 common from here, now they wanted to confuse you, so they wanted to make you hit that none, okay. So one more last step and you'll reach this answer, okay. So if you take 2 common from here, you'll reach root 2 plus pi by 4, okay. So I took 2 common from here, there was no 2 over here, so I divided this by 2, okay. So pi by 4, so option C is the correct choice over here, okay. Don't be in a hurry, check the options correctly, okay. So we just found out the field due to all 3 elements and just added them up, right? They were in the same direction, so just added them up. Keep in mind that here r is the perpendicular distance, okay, not this distance, it is the perpendicular distance from point O, okay. We found it out using some geometry, and yeah, we found out the field due to this quadrant and we just added that up, we got our answer. Over to the next question. So question 16 over here, this is your homework question. You can pause the video, take a screenshot if you wish to try it later, okay. So as you can see, this is a question from moderate to difficult category, and I personally believe that this question should not be a part of your BITSAT. It is slightly tricky, although it was asked in BITSAT in 2017, okay. It should not be a part of your BITSAT. It's a bit tricky, okay. Although it's a standard question, if you know it through coaching or somewhere else, so through some other means, then well and good, you'll be able to do it. But if you don't know, you have never solved such type of questions, then I believe that you won't be able to do it, okay. Anyways, I'll make the text solution of this question available on the website. Till then you can try it by yourself, okay. If you're not able to do this, it's okay, it's completely okay. You had a good run in today's class. I hope you enjoyed today's class. If you did enjoy today's class, smash like, subscribe. Keep enjoying physics.